Let's discuss a question from spring mass damper. This is a question from vibration. So if you have a spring mass damper, okay, the ratio of consecutive amplitudes is given. So this is free vibration, okay, with damping. Okay, so when we have free vibration with damping, and if you just perturb, give small oscillation and leave it, the oscillations try to die down, but they take a long time. Okay, so now the amplitude tends to decrease, and but it can be shown that from the equations, when you solve the equations of free vibration with damping, the equation is mh double dot plus ch dot plus kx is equal to 0. So when you solve this differential equation, and then you'll observe that we are not going to see here the entire derivation, but you observe that the ratio of the decrease of the amplitudes, the ratio of two consecutive amplitudes, that remains constant, and the relation is that ln a1 by a2. So a1 is some is amplitude, let's say, of first cycle, then a2 is second cycle. That ratio remains constant, and that ratio can be shown to be equal to 2 pi j root 1 minus j square. So this is again called as logarithmic decrement because this governs how the amplitude decreases. Okay, and what is J? J is damping ratio, and that is related to C, the other properties, as like this: 2 j m omega n, which is k by m. Okay, so this is again we define this relation when we solve this equation for different damping ratio. So that's about the theory. But now what is given is the amplitude ratio is given. The amplitude ratio of consecutive amplitude is 4.2:1, and then the period of vibration is also given. Now the period of vibration, remember the damping frequency is omega d, and the time period in terms of frequency is 2 pi by omega d. So this time is at the damping, that is given, and that is 1.8 seconds. From this we can find out the frequency of the damping. And one thing is that the what you need to know is that the omega damping is related to, if you don't have a damper, the natural frequency is omega n. So these two are related. So all these relations, the first one and the second one, these are again part of the derivations of this. So you got to go through the derivation and then come here. Okay, so now let's use the first one. First one we have to use to get the damping ratio J, and omega d from the time period we can get. So then we come to the second equation, we substitute omega d and J. J comes from the first equation, omega d comes from the third equation, and then we substitute and get omega n. And from omega n, again the time period is related, time period of natural vibration is related like this. So that is the flow of this problem. So let's first start and get the damping ratio from the first equation, ln 4.2, and that is 2 pi j by root 1 minus j square. So for ln 4.2, the value when you take the logarithmic in your calculator, it's 1.435, and that is 2 pi j by 1 minus j square. So now you take the square root and solve, you get j as 0.226. so that is the damping ratio. So now what we do is we get the time period is given, so we get omega d from the third equation, which is 2 pi by 1.8, and 2 pi by 1.8 is basically 2 into 3.7 so that if you can calculate, it is comes about 3.5 radians per second. Now we go to the second equation, which is this equation. We substitute omega d and we substitute the j which we calculated from the first equation, and then we get omega n, right? So omega n from this can be calculated, and that comes out 3.59. So not much difference from damping and undamping. Damping is very less because j is 0.226. okay, very less. Undamped, so it will take more time to dampen out the vibration. So okay, so time period. So now we got omega n. What we want is time period of natural vibration when damping is removed. So we substitute 3.5 in 2 pi by 2.5n, and then we get 1.75 seconds. So 1.75 seconds is the time period for one single oscillation. Okay, so 1.75 is the answer. Thank you. So we have used almost all the equations that are required for this free vibration with damping. Thank you.